Hello viewers and my dear students. Welcome to session 5 on thermal analysis. Here I'll be showing you a demo on 2D heat conduction problem in a plate. Okay. Now you see here the plate is like this. This is 10 meters in length, this is 20 meters in length. It is subjected to 200 degrees centigrade here, 100 degrees centigrade here, 100 degrees centigrade here, 0 degrees centigrade here. No convective heat transfer here. It is only, as you see here, it is only conduction. Okay, it is only conduction, and I have given you also. This is the plate has a thermal conductivity of 401 watt per meter degree centigrade. Also, I have given. Okay. Now here I have asked you to use plane 55 element. Okay, and I asked you to draw the temperature plot, thermal flux plot, vector plot, and showing rate of heat loss to the from the plate to the surroundings. Draw also graph of variation of temperature along the top end of the plate and all that. Anyway, these things we'll do. But the important thing what you should understand here is this is 2D conduction, because as you know heat always flow from a region of higher temperature to lower temperature. In the previous 4 sessions, what we were doing, it was pure 1D conduction because the heat was flowing in only one direction. But now it is 200 here, 100 here, 0 degree and all that. The heat flows not only in X direction but also in the Y direction. That is why it is brought under 2D heat conduction problem. Okay, it has only thermal conductivity given. It is pure thermal conduction. You have to assume, and you have to do thermal analysis of heat conduction. Okay, and you have to find out all these things. Okay, now as you see here, the problem is, you see here, as usual, you start a file, change job name. Okay, you write a fresh log file for this. Okay, so that whatever the log file created will be exclusively this Gurudat one, and you can copy and paste it in the editor, which I've shown it in the earlier sessions and all that. Okay, this can be done. That is, this is another method. That means copying the log file and pasting it into the command Ansys command prompt and executing also is another method. But what you should know here is this is a purely this analysis what you are doing graphic user interface. This is called GUI method of doing, not using log files. It is graphic user interface. We'll use the commands given in Ansys. Okay, we'll use the menus and we'll finish the problem. Okay, next file, change title. In that way, here what I'll do here is I'll write 2D heat conduction. 2D heat conduction in a plate. Okay, just I'll give the title and just fit it, and 2D heat conduction in a plate, that time everything you got, and this is all I am creating a separate log file under Gurudat 1. Okay, this is there. Anyway, these are all the basic things. Now you see here, we'll start with our analysis. Preferences, thermal you write, because it is a thermal analysis, thermal you say, just say okay. Then under preprocessor, element type, okay, you add, edit, delete. This add thermal solid. This quad 4 node 55 will support our analysis. The different elements what we'll create later on under meshing, each will be quad 4 node 55 or plane 55 elements. Okay, just say okay. Okay, then options and all that you don't worry, because we'll always take thermal flux and all that. It's per unit area. Okay, we always get thermal flux only. Okay, in that way, don't worry about the thickness. If you want, if you give the thickness in 3 dimension, you can see the thickness. Otherwise, there is no, the answers won't change if you give the thickness and all that. Okay, this just say close. Okay, then material properties you go, material models you go, thermal, conductivity, isotropic, This has a thermal conductivity of 401. 401 watt per meter degree centigrade. This you take, this is okay, you say, then material is exit. Unlike the previous problem, you have only one material here, okay, only one material, and now you do the modeling part, okay, modeling, create areas, rectangle by two corners. You see here, when you create rectangle by two corners, origin x and y 0, 0 you take, width is 10 meter you take. This is 20 meter you take. See here, and why I am taking in meters only because the thermal conductivity I have entered in 401 watt per meter degree Kelvin. Okay, I have taken their watt per meter. That is why the modeling also you see that it is in meters. Okay, width is 10, height is 20. Just say okay. Okay, this is the model. Okay, now you see here, once you have this, okay, then meshing, mesh attributes, if you go here, even if you go picked areas, no, okay, it is only one material has been defined. That is why you don't have to worry about that. Just say okay, because there is only one material. That's why so many times what you do, only one material, you don't have to assign different materials for different areas here. There is only one area that has a thermal conductivity of 401 watt per meter degree centigrade. That is why that is so many times what we do, mesh attributes, default attributes, plane 55, only one material is defined. You see here, only one material. You just say okay. Okay, don't worry about assigning different materials for different areas and all that, since there is only one area. Okay, now size controls. Size controls I have told you, you can have, you do by any method. Manual size you do, lines you do, okay, picket lines you do. See here, this and this, we will have some 10 elements, number of divisions 10. Okay, you just said 10. That means this is divided into 10. And picket lines, this and this you take and you make it as 20. Okay, 20. That means here 10 you have, here 20 you have. Okay, that means in each element, here in this, this is 1, here 20 elements, almost 200 elements are created here. Okay, now once you do mesh, areas, free usage, just free meshing, you just say pick this area, just say okay. Takes time. Okay, now as you see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here, and 20 elements here. That is 20 into 10, almost 200 elements are created. It's a coarse mesh, not a fine mesh and all that. If you take fine mesh, sometimes it takes more time for solving. Okay, now I told you this particularly. There is one convergence which I'll be talking about that later on. That is, what will be the ideal elements to choose? Okay, now I have chosen 200 elements. If you choose 300 elements, accuracy will be much more better. 400, it will be much more better. In that way, we'll do the convergence and say for 400 or 450 elements, your results accurate, the accuracy of the results will be very good and all that. But for the examination purpose and all that, you don't have to worry too much the convergence and all that. Directly mesh it. Okay, this mesh should be clearly visible. Okay, clearly don't make very fine mesh and all that. This is 10 here, this is 20 here, this you do. Okay, once you do this, see here, now I'll give the loads here. Nowadays, this is pre-processing is over. Now I'll go for the that is solution phase. First loads, define loads, apply thermal, temperature on lines. You see here, on lines means on this line and on this line. As you see here, this line and this line, you have a temperature of 100 degrees. 100 degrees, correct? No? This is okay, say. That means on this line, you have maintained a temperature of 100 degrees. Okay, then apply thermal temperature on lines. You take this line and say okay, and temperature here will be 200. will be 200. You just say okay. Then thermal temperature on lines, carefully see, you pick this line and say okay. And here on the right side line, you have a 0 degrees. Whatever is that given, just say okay. Okay. Now these are all the thermal loads. See here, there what we are giving. Okay, earlier in structure analysis and all that, this pressure loads and all that, what we are giving. Okay, UDL you are giving and all that. Here, thermal loads are so many things are there. Okay, that heat flow, convection, heat flux, heat generation, radiation. These are all the thermal loads what you can apply. Okay, like their uniformly varying load, uniformly distributed load. Okay, pressure loads and all that. In the that is even tensile stress, compressive stress, and all that. Like that, here what you should know is these are all the thermal loads. Out of that, I have given only temperature here. Okay, temperature only. In next problem and all that, we'll give convective heat that is convection, the load on that is convective heat transfer rate to be found out. There, this load that is load of convection also will give. Okay, that is now it is only here, here and here I have given 100, here I have given 200, here I have given 0. Okay, now there is no convective load here. It is only temperature load is there. Okay, now once you do this, okay, now you go for solution. First you check analysis type, new analysis, you should be steady state analysis. Okay, okay, now solve current load step you do. Once you do current load step, you should get the answer. Solution is done. You see here, solution is done. Once you get, you are more or less, you can be rest assured whatever you have done is perfectly okay. Okay, the solution is done. You got. Once you have got the solution, then the solution phase is over. Now we'll go for post-processing phase. That means presentation of the results. See here. Now you see here plot results. Under plot results only, contour plot, nodal solution, okay, DOF solution, nodal temperature, you just say, okay, see here, now this is what, this is 200 degrees, okay, heat is coming this way, can you follow? I'll show you in vector plot also. This is 0 degree, and you can see this greenish and all that, almost 88 and all that, though it is 100, it is flowing from region of higher temperature to lower temperature. Even here it is flowing from region of higher temperature to lower temperature. Okay, this is the temperature plot. Without forgetting, you have it plot controls, write meta file, invert white and black, and you call it as a temperature plot. That is the first plot what you get here. Then nodal solution you go, thermal flux plot you go, thermal flux vector sum you take. Now in this way, this is the thermal flux plot what you got. This is another thing what you note down, and this is plot controls again. Write meta file, invert white and black, and call it as thermal flux plot, and again store it in the paint. Okay, these are all the things what you need to show it to the examiner. Okay, then you see vector plot you take next one, predefined. Okay, thermal flux. You just say okay. Now you see clearly, see this is the region of 200, this is the region of 100, you see here, this is the region of 0, and now this arrows and all that will indicate how the heat is escaping to the surroundings. Okay, this is the red one, you know, red one what you give, you can clearly say almost 61,833 watt per meter square of heat energy being escaped to the surroundings. Okay, you see here, even here it is all 100 in this bottom, no, it was 100, it is escaping, that is, it is escaping through this. That means heat, only little heat is escaping here because 200 to this, okay, 100, from 200 is higher region, this is 100 region, little escaping through this, that is only this, but maximum heat is being escaped through this, okay, red region. Okay, this is 200, this is 0. In that way, you are seeing so much of heat is being lost to the surrounding. Okay, We'll continue this in